All right, welcome back, everyone. It's so nice to see so many of you. I know this is an annoying thing that I'm sure all your professors are saying, but we kind of lost 2 Mondays this quarter because of the weird Jan 1st being on Monday, and this upcoming Monday is a holiday, if you didn't know. There is no school on this upcoming Monday. Yes, go celebrate Dr. Martin Luther King by giving back to your community, or sleeping in, because that's giving back to you. So we got to get through a lot today. We're going to move through this warm-up pretty quickly, but it's in the same format as what we did last time. Here's a scenario. First, select the right type of functionality, list, stack, or queue, and really think about the difference between list, stack, and queue. It's about the order in which you maintain the elements. It's about the order in which the elements go into the structure and the order in which the elements come out of the structure. And then thinking about what you know to be the thing you want to optimize for. Again, this is your exercise in empathy. Would you implement it with an array underlying, or would you implement it with linked list nodes underlying it? The poll everywhere should be live. Go ahead and take 3 minutes, discuss with those around you, meet a new human, introduce yourselves, be the change you want to see in the world. We'll come back in 3 minutes. Go. All right, let's chat about it. Hopefully you've entered your vote, your submission on Poll Everywhere. I'm going to pop over and look at the Poll Everywhere in a second here, but before we do that, does any brave soul want to raise their hand and offer to us what their ADT then implementation choice was and perhaps why? Remember, there's maybe multiple right answers as long as you justify. Yeah, there in the middle. I'm sorry, can you speak up just a little bit? It's tough to hear. Yes. Okay. So we've selected Q as our ADT because, you know, we sort of have hopefully the first thing sent to the printer is maybe the first thing printed. And then we selected linked because maybe we have a hugely varying amount of jobs at the printer at any one given time. Like I can imagine we're, say, in Odegaard, and you're trying to print something out right before you rush to class. Maybe there's a bunch of things going to the printer, and then after class starts, there's nobody waiting in line for the printer. So you could have these massive variations, and maybe linked lists are a little bit better at adjusting the size of it. I agree with all of those things. I know there's other correct answers to this. Anybody have any other points of discussion or suggestions? Yeah, way in the back. Mm-hmm. Ooh, I love this, thank you. So we could also think of other scenarios where maybe it sounds like we're sort of still thinking about queue, but instead of using the linked list underneath, what if we used an array? Because maybe we recognize that there is a maximum number of print jobs we want to allow into the queue. We don't want that queue to get to like you're waiting days for your print job or something like that. And if we have a maximum capacity, well then the array is an underlying structure. It might be a really great option to optimize for that and give us that setting. That's a great way to think about it. Yes? Yes, also correct. You could technically implement it also with a linked list. And in that scenario, the question is, well, do I care about the optimization I might get from using an array and that contiguous memory to loop over it versus the optimization of maybe letting it grow and shrink? And I think that'll then come down to a capacity conversation that you and your computer have as to what's really going to be the most efficient, a array with a limited capacity or a linked list that you only allow to grow based on an if statement with the field. And frankly, you could do both in both scenarios. I love it. This is exactly why I said there's lots of multiple ways to go about this. Always think about what are you trying to enable, and also think about what is something you want to prevent. I love this idea that like we want to prevent the queue from getting longer than humans are reasonably going to want to wait, right? So there's lots of things to consider when you're thinking about the way you're going to interact with this. Let's take a look at what y'all voted on. Okay, I'm going to do this, and then I'm theoretically going to hit present. I see. So 77% of you ended up on list Q. This is somewhat targeted in that direction based on the information that I gave you. But 15% choosing array Q, I think that totally makes sense, like we just sort of discussed. Shout out to those rebels. Array stack and array list, get it. There are absolutely ways to implement this using all of these things. If this was on an exam, just know that you're going to have to justify what you're optimizing for if you go with one of those, we'll call them the alternative implementations. Any questions on this? Okay, I am now going to exit this, and then I'm going to activate it because I know how to use the system now. Okay, so here's my little linked Q answer, but all of those things are technically correct. Okay. Some quick announcements. So, of course, reminder that Project Zero, the individual assignment, your first assignment is due tomorrow by 11:59 p.m. Hopefully you have everything set up and you have your GitLab and all of that good stuff. I know that there have been some setup issues for folks, but I also know there's a lot of really helpful ed posts. So if you haven't yet tried to set up your environment, you should do so now. ASAP, as a matter of fact, because you don't want to find yourself in a situation where you don't know how to fix your setup and the deadline is looming. Though I understand Thursday nights will probably be the stressful night in this class, I will usually host my own drop-in office hours on Thursday nights, but a number of you asked for one-on-one meetings, so I actually just expanded my one-on-one office hours this week. So if you couldn't get a one-on-one with me earlier, feel free to check my calendar now. I just added a bunch of stuff this week and next week for that. Keep in mind that the due date for P0 is this Thursday, but the late turn-in is open until Sunday. So that's where you could use some of your late days. You don't have to tell anybody. It's just Casey knows life happens kind of thing. But please know that you will not be able to turn in the assignment after Sunday evening. If something terrible has happened to you and or your loved ones, I hope not, send me an email. We can always talk about it. Exercise 0 officially released yesterday. If you've opened it up and looked at it, you might be like, Casey, I don't know what any of these things mean, because we're going to learn about them today and Friday. And in fact, I'm going to go over questions that look suspiciously similar to questions 1 through 3 in your exercise today and Friday. Usually I do 1 a day, but again, we lose a day because of MLK Day. So I'm going to do 2 on Friday, 1 today. And then there will always be a 4th question that's a little more designy, to be annoying and pedagogical, a little more synthesis-y that I expect you to figure out on your own. But you're always welcome. Talk to your TAs, go to section, talk to those around you. You just have to submit your own work for that. Those exercises will go in and out on Tuesdays, and they have the same up to 3 days late policy if you want to use any of your late days. And then reminder, I think I briefly mentioned it in a lecture on Monday, but we have added a new policy this quarter, and I will update the syllabus, where if you attend sections 2 through 8, those are the sections that pretty directly relate to the exercises. So if you attend all of those, we will drop your lowest exercise score. The TAs are sort of the leaders of your section, and they're responsible for capturing your attendance. So if something terrible happens and you can't make section during one of those days, email your TA and they will have a possible makeup for you. But please know that those are for, I am ill and I don't want to get those around me ill. Not necessarily, it is difficult for me to get to school on Thursdays type of thing. That's why it's not, attendance isn't graded. It's just a little carrot for you to go in person. Because it turns out community matters. Who would have thought? And then I have the link to the lecture thread here. Okay, great. Any administrative questions at this point? Yes? Yes, that is what I just mentioned. We'll have some exceptions for that. Yes. So email your TA. They will have an asynchronous if you can't make it here or there. Other questions? Okay, great. Okay, so we are now officially starting a sequence of pretty theoretical code analysis style of topics. I know it's not the most comfortable for everybody. I'm just going to be real with y'all. But we are going to give you a lot of practice. Your exercises is practice. Section is all about practice. We now have an ed lesson that's practice. So even if what I go through today, 1, will feel fast because I'm sorry, I lost a lecture, and 2, might just be confusing, I promise that as you hear these topics multiple times, it'll get clearer. But please, if anything I say is confusing, go to that ed thread, ask questions. We have a bunch of TAs in the room that are happy to write out all of those answers for you, and it's helpful for others. So, remember this slide. I do expect to have heard the term Big O. We talked about it in one class already, and it is supposed to be covered in intro briefly. But it's this idea that we have these sort of broad categories or classes to categorize how complex a piece of code is. We call them complexity classes. And it's this way to sort of group pieces of code based on how many instructions are going to get computed by your machine based on how many pieces of data you're working on. This will make more and more sense as we get into it. But remember, the constant complexity class is we do the same code regardless of how many things are in the array. Linear is maybe we loop over all of the things in the array, so that takes 10 loops if there's 10 items and 100 loops if there's 100 items. Maybe we have a nested loop and we are looking at one thing in the array and then checking it against everything and then looking at another thing and checking it against everything else. That nested loop, that gets us to the quadratic complexity class. But what I just listed off there is sort of these basic patterns that maybe we started to pick up in intro. From here on out, we are going to talk about how to mathematically write functions for how to get to exactly how many operations your code will compute and then how to reverse engineer the Big O from that. So that stuff that I just listed, that's maybe some stuff you memorized. We're going to talk about the actual process now of how to get to what complexity class your code falls into. Okay, so how do we get from code to big O? Well, one thing we could do, and every student asks me this, is, well, like, why don't we just run the code and like stopwatch timer it? These are graphs. These are from my Surface Pro, so these are really old. But these are graphs of where I took the time to add a single item into a collection for either a linked int list, an array int list, and an int search tree. So it's just the time to add something to the end of those things. So you can see that there is some kind of patterns here. It kind of takes the longest to add to a linked list. It kind of takes the second longest to add to the search tree, and then it kind of takes the fastest to add to the array, even though there's kind of like some suspicious spikies going on in there. But it doesn't look all nice and like linear like we know it's supposed to be. I think the contains is a really good example here, where we can kind of see that there are some situations where, oh, like we can pretty quickly navigate these things. They almost look like they lay on top of each other, but there's these occasional spikes. And so if you can see, there's some basic relationships here between, oh, we can tell that, you know, what is this? Adding in like 1,000 items into a linked int list certainly takes longer than adding in 1,000 items to an int search tree takes not as long as adding 1,000 items into an array. But there is a lot of noise. This noise could be caused by a lot of different things. One, it could be caused by what's happening on my computer at the time that I ran these things. It could be caused by the size of my caches and the size of my RAM. It could be caused by, I don't know, did I get an interruption from the internet and then something started downloading? It could also be caused by, did I run out of cache space at a different moment in time? We're going to talk about that later in the course. And so all of these spikes are sort of an representation of how complicated and messy the real world is when we're actually running code on computers. And when we're talking about the complexity of code, we often don't know exactly what computer it's going to run on. We're often writing code that's going to run on a lot of different computers in a lot of different circumstances. So having a runtime analysis based on like Casey's Surface Pro at that particular moment in time makes it a little difficult to predict how these things are going to react out in other computers. So this is too reality-based. What we're going to talk about with Big O is we're going to lift out of the reality into the theoretical, and then we sort of get that apples to apples comparison because the theoretical might have slightly different impacts based on how fast your computer is, how much stuff you have going on your computer, how much storage space you have available on your computer, but I can't control that. That's you and your computer's business. What I can control is the design, so we're going to focus on the theory, not the practical. Cool. Okay, so meet algorithmic analysis. That's what we're talking about today. Algorithmic analysis is just a term for going from a piece of code through to something we're going to call a runtime function to finally get to the complexity class. So we're going to start with code. We're going to transform that code into a mathematical function in terms of how many pieces of data are stored in the structure you're working with, and then transform that into the Big O complexity class. The first step is something we call code modeling, and that is the act of going from the code to the mathematical function. So what we are going to do is we are going to very hand-wavy and at a high level attempt to write a mathematical function that counts the number of instructions your code will send to the computer as it runs based on different values of n. So let's look at this example down here. We've got a for loop, and it runs from 0 to n. And in that for loop, we assign one array index to be the value 1, and then another array index to be the value 2. You might look at that and be like, Casey, what a very boring piece of code. It just fills up array A with 1s, and it fills up array B with 2s. Yes, welcome to theory class. I'm going to show you a bunch of code that's essentially nonsensical so that we can talk about this. But the way that we would maybe think about the operations count is we know the loop is going to run n times. And we know that means that those two statements inside the loop, a at I equals 1, b at I equals 2, those are going to get repeated n times. And then we are going to count an assignment to be like one operation. I'm not going to get too deep into it, but if you kind of break us down from Java into, say, assembly, we're talking about sort of like basic instructions that are going into the CPU. The active assignment is just taking one number from one place in the computer and putting it in a different place in the computer. And the computer is really good at doing that. So that's sort of like one. Take this number, put it in this box. So within the loop, we sort of have a count of 2 operations per loop. The loop runs n times. So we have f of n equals 2n. Very high level. There's some other stuff going on there that we don't count. And I'm going to talk about those in more specifics. But yes, is that your question?
Yeah, I was just wondering if we're not counting the check of I less than n, is that maybe a waste of time?
Great question. Why aren't we checking I less than n or I equals 0 or I plus plus? Because technically those are bits of instruction happening too. In fact, it means somewhere in the computer there's a variable called I that gets assigned 0, and then it gets updated, and then it gets checked every time. And you're like, doesn't that count, Casey? Isn't that at least making it like, I don't know, 4n plus 2 or something like that? Yes, in a way, but here is this annoying hand-wavy thing. We are going to calculate these functions, and then we're going to just drop all the coefficients and constants anyway for reasons I'm going to explain. So we sort of hand-wave away some of those things. What are those things? Thank you for the segue. Here's what we decide we do count. So 1, we count what we would refer to as basic operations. That's anytime we do math on something, adding, subtracting, division. Anytime we do assignment, we take one number from one box, we put it in another box. Anytime we return, which is technically the same thing in assembly, it just takes a number from this process and sends it to this process. That's also 1. Anytime we access a box in memory, anytime we say array at this index, or, hey, give me this variable. That's also me just going somewhere into the computer to a given box and grabbing something. So all of those are sort of like one basic operation. Now, because it's Java, they might actually be multiple assembly codes, but your computer is so freaking fast that for the human understanding of how time is going to execute, we're going to all consider these to be essentially equivalent in terms of how long they take, which to us is so instantaneous that we can kind of, not pay too close attention to the specifics. So we start with the basics, and then we start to add up and multiply the basics based on the control structure they're in. So for example, a function call. If I, within my code, call out to a different method or use a function on an existing object, even though that might be a single line of code in my code, I need to know what's it doing in that method, and we're going to count up the operations in that and add it into my total. Same thing with conditionals. We're going to count whatever it takes us to do the evaluation, so whatever's in the if statement or else if parentheses, and then we're going to count the body of that statement should it be true. Now, keep in mind, we might not count both the if and the else body because those are mutually exclusive. So, spoiler alert, we may get to code that behaves a little differently. It might have sometimes really elongated runtimes and sometimes have really short runtimes based on the results of an if test. We're going to talk about how to model that. And then loops. This is the most annoying handy one, like our friend asked. We just kind of decide, we don't pay attention to the loop header. We don't count that. But we do use the multiple of how many times the loop runs. So we don't pay any attention to the time incurred by the I counter. We just sort of consider it negligible. And then we only count however many things are happening in the loop, and then we multiply it by how many times the loop runs. Let's look at another example. And I promise there's going to be a bunch of examples in section. You'll get more practice. I also will tell you there's more practice here in the lecture. I just can't have time to go over it because of that stupid Monday. But let's say we are modeling this piece of code here. I like to start with the basic instructions and then sort of work my way out to the control structures. So maybe assigning 0 into in sum, that's kind of like 1. assigning I to 0, that's 1. And then I kind of jump inside that while loop. I'm not thinking about the while loop yet. And I see like, oh, there's the I minus 1, that's like a 1 evaluation. We see there's an I times 3, that's 1. We add some to that, that's another 1. And then we assign the results of that into sum. So that line there is really like 3 all mushed together. Because we have to, the computer is going to do that in a sequence, right? It'll do the parentheses first, so it does the addition or the multiplication. Then it is going to do the addition, and then it's going to do the assignment. 1, 2, 3. That means we have 2 on that line because we do what's to the right of the equal sign first, that addition, and then we have the assignment, that's 2. And then, like I said, returns are counted as 1. Any questions on how I got these numbers for these basic operations here? Yes, please.
So in a conditional, you do count the header as one version.
What a annoying and inconsistent thing. You just contradicted yourself, Casey. Yes, you're absolutely right. I said ignore the for loop header, and then I just counted the while loop header. Yeah. Why? Convention? I don't know. Argue at some researcher. I promise there's not I swear I've looked for the historical reasons for this and I can't find them. Also, like I said, we're going to drop all of the numbers in a little bit, so you'll see why they don't really matter. But in this case, part of the reason I counted that while loop header is because you'll find sometimes that while loop header is doing really complicated things. Like while the stack is empty, which means go into the stack and maybe check what's in there, or while there's still things left to look at. So maybe there's really complicated stuff going on in that while loop check. That's why we count it. Whereas the for loop header, it's almost always just counting an int, so that's considered sort of negligible. But very good question. Okay, then let's work our way out control structures wise. Let's look at this while loop. How many times is this while loop going to run? Yeah, please. N times, absolutely. Oh, sorry, that's the summation. 6 is just 3 plus 2 plus 1 times n, how many times the loop runs. So that means that every time the loop runs, we do that check, we do the sum math, we do the I increment. So we get 6 operations happening every time the while loop runs. The while loop runs n times. So we end up with a function 6n plus, and that little 3 comes from these 3 things happening outside of the while loop. Questions on how I got to 6n plus 3? Great. Guess what? Next week we're going to do this for recursion. We're going to have so much fun. Okay. There is another example, but I skipped that slide. You can look at it on your own, but this sort of process still applies. So now we have gone from code to the code model. So maybe our code model is like 2n or it's 6n plus 3, something like that. But that doesn't look like a big O, right? So now we have to figure out how we get from that mathematical function to that complexity class. So what we are going to do is we are going to, quote, find the dominating term. And what that means is that there's a lot of stuff happening, but we really only care about the big O analysis when we get to massive scale. And if you've ever sort of graphed things, those constants and those coefficients, they like really impact how your graph is shaped when you have really small values. But as you kind of like go towards infinity, meaning as n gets bigger and bigger and bigger, and you kind of like zoom out and zoom out and zoom out on your function, those little coefficients, those constants, they don't really dictate the overall shape of the graph. In fact, the overall shape of the graph will be dictated by whatever term of n grows fastest as n tends towards infinity. If all of that was gobbledygook for you, don't worry. All you have to think about is, let's say we have a function based on a piece of code I didn't show you. So let's say we did the code model and we ended up with a function 9n plus 3 times n plus 3. I'm going to distribute that because algebra. And then what I'm going to do is I'm going to choose the dominating term. If I had a function 9n squared plus 3n plus 3, the shape of that graph is going to be dictated by that n squared. It'll give you that kind of curved, quadratic type of shape, because that term grows so much faster than the plus 3 at the end. So the plus 3 at the end just kind of becomes negligible, and we just kind of throw it away. And in fact, we end up even throwing away the coefficients, because when we compare 9n squared to 3n squared to 2n squared to even 10n squared, like they all end up having generally the same shape. And if we tend to n towards infinity, eventually at a certain scale, all coefficients of n squared will kind of start to look like they lay on top of each other. Again, if none of that matters, it means find the biggest term of n, delete all of the constants, delete all the coefficients. So you get to that n squared, and that means, hey, we're in the complexity class of O of n squared. Questions? Yes?
This makes sense for like for loops being increments of n.
Sure.
What about like log?
What about log? That is a great question. Let's see, do I have anything helpful? Maybe not. So when it comes to logarithmic graphs, they kind of grow rapidly at first, and then they start to like level out. What that usually means in terms of code is the amount of things you're searching through, we reduce in half and in half and in half. So let's say we're looking for a word in a dictionary. If the dictionary only has like 10 pages, we're going to look at the middle, and we're going to decide whether that value is in the front part of the dictionary or the back part of the dictionary, and I'm essentially just going to ignore 5 of those pages. And then I look at page 7 or something, and then I ignore 2 of those pages. And so the difference between eliminating 5 and eliminating 2, those look really big in relation to each other. But as those values get really big, when I say like have a dictionary of 1,000,000 items, that first cut, cutting it in half to 1,000,000, and then cutting 1.5 million again, the rate at which that change happens sort of levels out over time, because we're making these in half type of decisions. Another thing that will come up a lot in the logarithmic class will be when we're navigating through a binary search tree. Because essentially what we're doing, and we haven't learned about these yet, so don't worry, is we're going to look at a node and we're going to ask, do we go left or right? And if that tree is a full tree, we kind of eliminate half of the nodes. So the logarithmic class, you'll find, comes into essentially play whenever we are looking through a set of data and we're eliminating half of the possible options at each run. And I say half because we as computer scientists, when I say log, I mean log base 2. I know we should say log base 2, and I'm sure there's some chemists somewhere in here that are like, no, natural log, but I mean log base 2, and that's what you'll see, the sort of cutting in half. And we'll get more into that as we see some of those structures. Yeah. Yeah, I think when you say, is it additive, like let's say we're writing a function for the array list, and in that function we want to search through everything in the array, and then we want to insert something at the place that we find. We need to add the function or the amount of operations it takes to search, plus the amount of operations it takes to shift, plus the amount of operations it takes to actually insert that thing. I don't know if that's really adding, but yes, exactly. Yeah. Okay. Great. This stuff here, this is me attempting to kind of show to you why we can drop those coefficients and those constants. So like here is an example of f of n versus like g of 4n. You know, 4n, this red line here, looks really dramatic compared to this f of n line at small values of n. But as we like zoom out, they start to look like they just kind of lay on top of each other. That's part of why those coefficients don't really matter. They're still growing at the same overall rate, like that linear rate, that relationship. So the coefficients don't really matter that much. And then n squared, we can see it really looks like it almost always grows faster than linear. So like what this would mean is that a piece of code that runs in n squared time is always going to take longer than a piece of code that runs in O of n time. But if you're like me and you're like, Casey, that's not technically correct, because there are moments where n squared could actually be less than n, I would be like, oh yeah, you're right. What I care about is not that this O of n squared is always slower than linear, but is it slower than linear as we tend towards infinity? Thus, leading us to the formal definition of big O. Here we go. We've got an actual mathematical definition. So the definition of big O is f of n is in the O of g of n if there exist positive constants c and n naught such that for all values of n greater than n naught, f of n is less than some constant times g of n. Do you have to understand that? No. I'm just giving you the mathematical definition. I'm going to explain to you what this means in human language. And what this essentially means is big O is an upper bound. It is something that should tell you what is the absolute top growth rate of the code you're working with after a certain moment in time. That n naught thing is to like handle that exception of like when n squared occasionally dips under n. You know, like I put it here, right? Like this moment in time right here is n naught. And so you can see after this moment in time, f of n will always grow faster than 10 log n. So we only care about as it tends towards infinity, and that's because we added this n naught piece into the mathematical definition. Let's look at some more examples. Again, if math makes sense to you, here you go. If math doesn't make sense to you, don't worry about it. You don't have to memorize this piece. But essentially what we say is that when we're talking about big O, we're talking about some complexity class that will always dominate or upper bound your code's runtime function. So here is a suspiciously close to exercise 0 question. Let's say I have a graph that is very poorly drawn by past Casey that looks like this. It kind of starts here, and it starts kind of quickly, and then it kind of levels out. Can anybody guess what complexity class this runtime function is in? It is not a trick one. I'm not trying to trick you with this one. Yes, please. Logarithmic. Absolutely. This just has that logarithmic shape. Logarithmic kind of starts faster and levels out over time. It never technically hits flat, but it seems to get closer and closer. It asymptotically sort of extends out flat. Logarithmic runtime. Okay? How about this one to the right here, where it kind of starts pretty fast and then only gets faster. In fact, it kind of goes asymptotically vertically in a way. Does anyone know which one that one is? Yeah, way in the back. It is a type of exponential. It is n squared. So we've got n squared, and that's going to start fast and just get really fast. Is this a little bit of me just reminding you of what these graph shapes look like? Do I have to look up what the graph shapes look like before I teach this? Yes, I do. Well, that's just what a logarithmic looks like. It asymptotically starts to level out, n squared, or anything n raised to the power asymptotically goes up. It also looks very similar to the exponentials, which might be a constant raised to the value n. They all have the kind of that shape. And I will tell you, all are in a what we would consider inefficient complexity class. In that little big O picture that I showed you at the beginning, it had like green, yellow, or green, orange, red. This is a red. Okay. What about this sinusoidal? Well, that's confusing because it has different rates of change as it goes along. But that definition of big O is that I am looking for a value that always upper bounds the growth of my function. So the way that I would approach this on your exercise is, you know, in those other color, this is green, for those of you that are colorblind, I just sort of drew a line that upper bounds the very top of it, and I drew a line that lower bounds the top of it. And then I only care about those bounds. I'm kind of throwing away what happens in the middle there. I just want to know what complexity class upper bounds this. So instead of looking at the red line, look at the green line. What complexity class upper bounds this one? Yes, please.
Constant?
Constant. Because even though it's sinusoidal, it's going to go sinusoidal until infinity, meaning as n gets bigger, the growth rate doesn't seem to be impacted by that. the growth rate maintains a constant upper bound. Okay, we've got another one here, where again, we've kind of got, and you maybe kind of, this looks a little like the graphs I showed you at the beginning, where it's sort of like, looks like it's going up linear, and then there's a spike, and then it goes up linear, and then there's a spike, and then it goes up linear, and then there's a spike. So there's kind of like, again, I drew this green line on the upper bound of those, and then I drew another line on the lower bound of those, but I don't care about what happens in the middle, I just care about those bounds. Can anyone tell me what complexity class this falls into? Yeah, linear, exactly. Again, I'm just like, what is the worst case in this? Ooh, that was dangerous. What is the like slowest runtime? Linear. It's linearly increasing those spikes. And technically, the bottom is linear too. It's just like maybe a different coefficient linear. But again, those are all in the same complexity class. Okay, and then we have this one on the bottom where we've got what looks like a linear runtime, and then something happens in the code, and it seems to shift to this like, it starts fast and then kind of levels out runtime here. Now remember that definition of big O. Even though this looks like it has two different rates happening within it, I only care about the rate as it tends to infinity. So what is the complexity class of this one? Yes. Yes, absolutely. Because that linear piece there stops at a certain point. I don't care what happens about that. I only care as n tends towards infinity. Questions on this piece? Yes? N log n looks like a slightly bigger and thus slower logarithmic growth rate. I want to say I have posted somewhere a picture of all of the different like sort of shapes to them and things like that. But I am also not going to lie, if you can't tell from the other pictures, I just plug stuff into Wolfram Alpha if you forget what the shapes are, because I do not own a graphing calculator anymore. Any other questions? Yeah, in the back. Yes. Yeah, exactly. It's the and not moment. That's me trying to demonstrate to you why we care about that big O definition. Yes? Whoa, what if the upper bound and the lower bound aren't the same complexity class? What a fabulous question. Before I go to the slide that answers that exact question, does anybody else have any questions on this one? Yes? Great question. That's where we're headed. Here is a code model, and I'm going to do this. I'm going to show you this one. I don't have time to walk through it, but this is a piece of code that determines if a number is prime. So what this does is in order to determine if something's prime, I take the value n, I start from the value 2, and I check, does this 2 test number fit perfectly into the number I'm trying to determine if it's prime? If that number is an even number, I find out that it is not a prime really gosh darn quickly. If the number is a prime, I got to check everything up to its square root minus the remainder to determine that it has no clean divisor. So it takes the most amount of while loops to determine something is prime, and it takes the least amount of while loops if, say, it's an even number, because I real quickly determine it's not a prime. That's what the code's doing. You can look. And so it's sort of like, okay, well, that's kind of a linear thing. You know, the larger the number, the more while loops, the bigger its square root is. But sometimes it bails out of that loop really, really quickly. Sometimes we hit this return false, and we end really soon. Question? Yeah, sorry, square root of n, and then I'm doing that annoying thing where I'm like, coefficients, square root of n is still in the n complexity class. So what do we do when we have this? Well, one, let's graph it. Maybe that helps us. So this is a graph of how this runs. And so you can see that all of these here, these are prime numbers. It took us a long time to figure those out. But technically what's happening is I'm like, ooh, that was an even number, prime number, even number, prime number, even number, prime number. And so I kind of get this like big squiggles where the bottom seems to stay flat, but the top seems to grow at a linear rate. So it feels like if I said this code runs in O of n time, I'm not getting the complete picture. Because sometimes it's O of n. You can look at that. These things don't feel equivalent. So wouldn't it be nice if I had a way to define both the upper bound and the lower bound? Welcome to a new definition. This is big omega, where it is exactly the same definition. Where's my mouse? There we go. But look it, I have switched the alligator mouth. That's a technical term, I'm sure. So big O is the upper bound of your growth rate, your function, and omega is the lower bound. Okay. Oh, here, thanks, Pass Casey. So we can see, big omega plots, those fit underneath that line. Big omega is the lower bound. So if I had a function 2 to the n cubed, and cubed is a lower bound, and squared is a lower bound, n is a lower bound, constant is a lower bound, those things all fit underneath my growth rate. So 2 of n cubed is lower bounded by all of those. But you might be like, Casey, I just want to talk about that n cubed. Technically, the definition did not say tight. It didn't say fit. It just said lower bounded. So all of these things are true. All of these values are technically in the omega of 2 of n cubed. And you're like, no, Casey, that's not what I meant. I meant the right fit on top of it. Yes, question? Wow, what if we were like, how do you find the fit? What a great question. So what we're going to do is, if the big O and the big omega are the same complexity class, then we decide that they're this fit. It's like, that is the thing. If the big omega and the big O are the same complexity class, then its fit is that class. But again, this prime runtime function is annoying, and it doesn't seem to fit into that category. So how do we find that sort of in the middle type of thing? That is called amortized analysis. It is something, if you say get into the CS degree and you go take 332, I think they do a little amortized analysis 332. Yes, thanks, CS majors. So I'm not going to get too deep into it in this class. Instead, on what's today? Wednesday? On Friday, we're going to talk about something called case analysis, where we talk about, at what times are we going to pay attention to the upper bound, at what times are we going to pay attention to the lower bound. But it does feel like we need a third definition, because why not? And look, here is that fancy math definition, where what we've done is we just took the definition of omega and put it to the left of f of n, and the definition of O, and we put it to the right. And we're like, what sits in the middle? Big theta you can kind of think of as the equal to the fit. So if the big O and the big omega are in the same complexity class, that's one of them. Oh my gosh, I am going to make this in these 2 minutes. I'm going to do it. But what about that pesky prime function? What if the upper bound, aka the big O, and the lower bound, the big omega, what if the tightest ones are not the same? That means the theta doesn't exist. So a function will always have a big O, it will always have a big omega, but it may not have a big theta. Do I have it? Yes. So here is a summation of those three definitions. You're going to get a lot of practice with these definitions in section tomorrow, where we sort of look at different functions, decide what the big O and the big omega and theta are. And I do not have time to go over it. Oh, great. Thanks, animations. But here is a great page that you can look at in your own time so that you can understand how to apply these definitions to different functions. Sorry that was so fast. Darn those Monday holidays. Come back on Friday. We're going to get into case analysis and definitely go to section tomorrow. I promise the TAs will make this a lot clearer. Thanks so much, everybody. Isn't math fun?